My name is Brian Larkowski. Today I'll be talking about the evolution of heat recovery ventilators. As we approach the year 2020, heat recovery ventilation is becoming increasingly mainstream in all areas of residential construction as it resolves multiple issues. It is the backbone of systems that provide occupant health and comfort. In dealing with countless architects, engineers, trade professionals, and knowledgeable homeowners, we felt the need to better explain the evolution and revolution of heat recovery ventilation in North America. In the first half of the 20th century, energy was inexpensive. Homes were typically built without ample consideration of air sealing. These drafty homes led to a modicum of ventilation leaking through the walls, floors, attics, windows, doors, etc. It was a poor efficiency model, but ventilation was actually better than most homes today. In the 1970s, we experienced the energy crisis. Gasoline was being rationed across the country and prices skyrocketed. This affected the prices of other forms of energy as well. It was the beginning of the end of cheap energy, and the home building industry was beginning to feel the need for improvements that reduced energy consumption. In the late 1970s, Johannes Kirchmeier developed and patented heat recovery ventilation technology to conserve energy while simultaneously addressing indoor air quality. He may have been a little ahead of his time, but he was on the right track. In the 1980s, as part of evolving conservation technology, windows made serious improvements in air tightness and glazing that made them much more thermally efficient. This was a major step in the evolution of tighter envelopes that would provide thermal comfort and energy conservation. Sometimes in construction, when we fix one problem, we inadvertently create another. As tighter envelopes began to address thermal efficiency, they also began to seriously degrade indoor air quality. This was a time when the public was becoming more aware of the dangers associated with secondhand smoke, radon, and other things that were proven to negatively affect the health of the occupant. These pollutants became concentrated within the tighter envelope. Most homes were using forced air furnaces that provided high flow, high velocity circulation of air while heating and cooling this air. What was not adequately considered was the fact that these systems provided no ventilation. They just rolled air around in a circle of supply and return within the home. If someone had the flu or a cold or other airborne related disease, it was spread throughout the home and other family members were directly affected. People began to look for cheap ways to ventilate. At the time, we thought that exhaust-only ventilation was the answer. Whole house fans were used to provide ventilation on optimal days. They also agitated particulates that negatively affected occupants with respiratory sensitivities. They made homes dustier and did not provide continuous ventilation. Many construction professionals are still clinging to this concept by using continuous bath fans. This may be a cheap and easy fresh air strategy, but what are we doing? Where is this air coming from? Attics that contain dust, insects, and rodent droppings, crawl spaces that are dark, damp, and dusty. Negative pressure results in uncontrolled air and moisture are pulled into the home through walls and insulation. If the goal is to enhance indoor air quality, this is a serious failure. By the way, there is no energy recovery involved. We reached a time when we needed to reconsider Mr. Kirchmeier's invention of the HRV. Now let's look at the same house using a different ventilation strategy. We'll use an HRV to provide continuous fresh air ventilation. Exhaust ventilation is still implemented in areas such as kitchens, bathrooms, and laundry areas, but the system is balanced with fresh air being supplied to bedrooms, living room, and family room. Air is filtered to a high level, and heat or cooling are recovered from the outgoing stream and imparted to the incoming stream. New technologies such as HRVs evolve significantly as they become mainstream. Questions arise such as, how much power is consumed in saving the energy within the home? Is it a positive equation? If the HRV is too loud, occupants have been known to see it as a nuisance and turn it off. Other relevant areas of concern are level of filtration, level of airflow, bypass options, and durability. If we fast forward to 2019, The evolution of heat recovery ventilation has advanced dramatically. There are units such as the Zender Q series that have efficiency above 95% with lower watt draw, higher level of ventilation, better filtration, and features that allow for automated bypass of the heat exchanger when conditions outside are favorable to those inside. These units are durable, easier to service, and include sensors that provide data and alerts that pertain to maintenance, such as filter replacement. They also have the ability to communicate and integrate with other components or systems, such as radiant conditioning or dehumidification. We want to reiterate the difference between conditioning and ventilation. Forced air units are an example of conditioning. These systems roll air around the circle, providing heating or cooling. This is done at high volume and high velocity to supply and return large amounts of air. Ventilation systems like HRVs provide continuous, balanced fresh air to the occupants. They do not provide heating and cooling, but conserve the energy that conditioning provides. These are low flow, low velocity systems and require smaller ducting that is designed to optimize distribution of this fresh air. Let's analyze the impact of forced air units on indoor air quality. Even though forced air units filter the air, they deliver this air intermittently and at high velocity. This agitates airborne particles that create issues for people with respiratory sensitivities and aggravate allergies or irritate the eyes of those within the space. HRVs typically filter the air at higher levels as air is moving more slowly. The slow, deliberate, continuous supply reduces airborne particulates and results in a cleaner home. Balanced ventilation means that concentrated airborne toxins are continuously removed and replaced with fresh filtered air. High velocity, high volume air provided by forced air units requires large ducting. Low velocity, low volume air provided by heat recovery ventilators requires smaller ducting to be effective. Mixing these systems is a typical practice in commercial projects, but it has a diluted effect. It is clearly better than no ventilation, but is certainly not an optimal way to deliver fresh air. The most effective way to deliver low volume, low velocity ventilation is via a distribution system matched to the requirements of low flow, low volume. It can also include sound attenuators, manifolds, registers, dampers, and trim components. These types of systems are proven to deliver predictable and reproducible results. Optimizing, regulating, and balancing flows of both supply and exhaust results in getting the most out of these HRV systems. Trunk lines deliver the air to the manifolds and sound attenuators. Trunk and branch ducting should be insulated. These larger ducts deliver air better over longer distances than smaller tubing. This means that a unit in the basement might need a trunk line run all the way to the second floor to minimize static pressure. It would then be connected to manifold boxes and smaller tubing running to register boxes mounted in ceilings, walls, or floors. Zender provides a system of engineered components that addresses controls, register boxes, damping, and even finish trim. By carefully designing these as a system, these systems can be commissioned and finely tuned to perform pursuant to approved designs. One of the most frequent questions we receive relates to the difference between HRVs and ERVs. The main difference is in the core or heat exchanger material. HRV cores are made from non-absorbent materials. They recover heat and require a drain to channel condensate. ERV cores allow for absorption and redistribution of humidity. They may have a lower sensible efficiency, but they also provide latent efficiency, so overall they're even more efficient than an HRV. They help to moderate humidity in both dry and damp climates. This slide shows the comparison between a standard HRV core and the ERV core when it comes to overall efficiency. The use of the ERV is becoming more prevalent as moderating humidity levels within the home also enhances occupant comfort and health. Since the ERV redistributes condensate, no condensate drain is required. To review, heat exchange happens in the core. Zender units are designed with interchangeable cores so that an HRV can be upgraded to an ERV simply by changing the core. The cores are also easily removable for cleaning and maintenance. There is a vast difference when you compare the performance of various HRVs on the market today. Even though Zehnder units have much more advanced features, the main consideration with a heat recovery ventilator is the heat recovery and the amount of ventilation. When delta T exceeds 20 degrees Fahrenheit, performance becomes quite clear. This is when an HRV should shine, not falter. The amount of CFM provided at a specified efficiency level is critical to optimizing indoor air quality. Better motors equate to lower watt draw, saving more energy, especially since these devices run continuously. ECM motors with lower watt draw are quieter as well. Even though Zehnder HRVs were widely known as best in class, the advent of the Q series has created an unparalleled level of efficiency. Zehnder units typically reduce loads by about 38% when compared with competing units. Zehnder is also the only manufacturer we know of that supplies a complete engineered distribution system to attain optimal performance. To review, HRVs and ERVs do not provide heating and cooling. They provide balanced, filtered, fresh air ventilation while conserving the energy of heating and cooling within the home. When installed properly, these devices conserve more energy than they use. ERVs conserve both sensible and latent energy recovery. We'd like to thank you for taking the time to learn more about the evolution and revolution of heat recovery ventilation. Please feel free to contact David Green with any questions or to get a free quote on your project. He is the Regional Manager of Zehnder Sales in California and the Southwestern United States.